Good afternoon. Welcome to Krishna's class. We continue with our exploration of the abstract integration theory. In fact, just recall that we proved the Rees representation theorem and then created the Lebesgue measure and Lebesgue measurable sets and Lebesgue measure on Arctic. Now, what we want to do is then, of course, we have the definition of what are called measurable functions and so on. So, let us put the background here. So, x we take as a locally compact Hausdorff space. X is a locally compact Hausdorff space. Then that's the first step. Then by theorem, there exists a measure space X mu where M is the set of all Lebesgue measurable or measurable subsets of X, and mu is the measure, which we call the Lebesgue measure. This is, of course, guaranteed by the Viswa solution. Now, this is the background in which we are going to make statements. In particular, we extended or constructed the Lebesgue measure Arctic. Now, it is a complete measure, and it is also the yeah. Just take this. Okay. So that is the background in which we analyze the relationship between measurable functions and continuity. So you see that the continuity plays an important role in the construction of Borel measures So what Borel sets are the smallest sigma algebra that contains all open sets. Okay? And you know that how continuity comes into play is, see, if you have f continuous, suppose f is continuous from x to, I mean, this is to y, where y is a topological space, then f inverse of what you call open sets V open y is measured. In fact, if if f is a continuous, sorry, if x is a topological space and y is a topological space and f is continuous, then you see that all open sets here are measurable, and you have, you know, the Borel sets, all Borel sets belong to this class. So that is something that is to do with the continuity, right? So it really plays an important role in the analysis of the construction of Borel measures, and especially Lebesgue measures. Okay. Now the question that we raise this stage, this is the question. A measurable function need not be confused. Need not be confused. However, when you ask the following question, how close it is to a continuity? To a continuity. Is it nearly continuous? This is the same question posed reposed in that. So this is the basic question that we are trying to analyze. Now there are two interesting theorems in this context. Because we are talking about continuity, we are talking about functions mapped from x to c or r, real valued or complex valued functions or x. Okay. Addressing this problem. The first result is the first one, Eugene's theorem. I am not planning to do the proof of this theorem in this lecture. We'll take it up in our next lecture, but qualitatively explain what exactly this theorem is. Suppose it's a short lecture. F is a complex value measurable function of the condition is that if you take open sets and take the pullback, it is a measurable set. That is the condition. Okay. Let and measure of A these are the conditions that you have for the statement of this theorem. That is in the complement of A in X, F is 0. That is another assumption. Now that gives all the ingredients assumed for in this theorem. Now then what it means, what it implies, we can connect this or with continuity in the following. There exists a continuous function, complex value function on X with compact support, that is CCX, the usual notation. a G belonging to CCX such that F is nearly equal to G. That is, measure of a set of points x belonging to x where fx is not equal to is less than epsilon. This is the first state. So no matter what your epsilon is, you can find a corresponding function g with compact support such that the measure of the set, the measure of the subset of x where f differs from g is of measure less than epsilon. That means almost everywhere you see that there is a continuous function which is equal to f. Further, we may choose G such that this is a bit of a technical thing. Supremum of x belonging to x x belonging to x. So this is the statement of the theorem. Now what does it say? Now this means this says that for any epsilon positive, on the complement of a set of measure less than epsilon, f may be f is continuous. See, that means, you have another continuous function which agrees with f everywhere except on a set whose measure is less than. Let's take one sample. Now let us look at one example. Let interval 0. Okay. Go. Chi of Q complement. What does this mean? It is equal to 1 at all rational points, 0 at rational points. Now, look at this function. Now, how do we choose the function g? Choose g gx and g is a continuous function. Then g is a continuous function. Now, the set of x where this is equal to the interval 0, 1 at the rational points. And g is a continuous function. This is at the rational points. This is different. This. And then you see that the measure of Lebesgue measure of this is equal to 0, which is less than epsilon for every epsilon. What does this mean? See, fx almost every. Okay. Where f is not a continuous function, but it's a measurable function. G is a continuous function, and this is merely a, or in fact, it can be looked upon as a part of a continuous function, and the set on which they differ is only can be made arbitrarily small. So functions g can be so chosen such that the set on which they differ is arbitrarily small. So this is an example. It's a very trivial example, but then probably give some insight because you see that this function is not Riemann integral. It's Lebesgue integral. Now I am going to discuss the proof of this theorem in detail in my next lecture. And one of the interesting corollaries of this result is the following. Corollary. Suppose further that mod fx is less than or equal. Then there exists a sequence Gn such that Gn belongs to the continuous function with compact support on x with mod Gn less than or equal to 1 and fx equal to Gn. Now there again you can construct an example using the very same theorem, because you see that the function that we are considering here satisfies this condition. Therefore, this theorem must be true, and you can actually try to find out what this Gn should be. Okay. Gn belongs to CCX. What kind of functions? It's quite easy to work out. Okay. Now we make a remark on this. These results imply that a measurable function is continuous everywhere is a part of continuous function differing from the given function on a set of arbitrary small measure differing from the given function continuous function. On a set of arbitrarily small function. That is the sort of relationship that you can establish between a continuous function and a measurable function. Now there is yet another result, very interesting. This is called the Italy-Caratio. We give the statement. Once again, we put off the proof for our next lecture or the lecture after. Suppose it's an L1 function with respect to the measure. F real value and epsilon. These are the assumptions. F is an L1 function, F is real value, and epsilon is positive. Then there exists functions U and on X such that U less than or equal where U is upper semiconductors and upper semiconductors and bounded above, comma, V is lower semiconductors and bounded below and F is squeezed between U and V the integral of their difference is arbitrarily small. Integral over X is less than. That means you see that this function f can be squeezed between two functions, one u and v, where u is upper semiconductors and bounded above. V is lower semiconductors and bounded below, and such that the difference between U and V is integration. Its integral over X is less than 0. That means they are nearly equal. Okay? They differ, they do differ, but they are nearly. So you can make this choice and make this choice or choose U and V with these conditions as closely as you want to the given function V. So we are seeking an approximation from above and an approximation from below. Okay. So and the difference between these two approximations integrated over the whole X is less than. That means they are nearly U and V are nearly. One is upper semiconductors, the other one is lower semiconductors. Now this is the Italic character of it. Now this is again, you see that you look at the conditions that you have. You have F now not by continuous functions, but one of them is upper semi-continuous, the other one is lower semi-continuous. Okay? Right? And this difference between them integrated over X is less than 0. Okay, thank you very much. I think I will stop here, and it's a very short lecture, but looking at the problem that I have stated earlier, how continuity and measurability are related. Here we are talking about semiconductor. Thank you very much. The proofs will be, of course, done elaborately for all these results in my next 2 lectures. Thank you very much.